And now in this lecture we'll find out the radius of the small circle. In the drawing we have a small circle that is inside a semicircle. We know that side CD equals to 3 units, side DB equals to 4 units, angle CDB equals to 90 degrees, and we want to find out the radius of this small circle. So we'll start with a construction. We will complete this semicircle to a circle. So we completed this semicircle to a circle. In the next step we will extend line segment CD until it touches, by a straight line, until it touches the circle and we will define the touching point of the extended line segment CD in this circle as point E. And actually here we extended the straight line CD by a straight line, and when you extend the straight line by a straight line, the result must be a straight line. So CE, that is the result of the extended of the straight line CD by a straight line, must be also a straight line. So I write it down. CE must be a straight line. Line segment CE is a straight line. And we know that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on this side of the straight line CE at point D, then the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So at point D, so which angles we have at point D, at this side of the straight line CE? We have here 90 degrees. Plus this angle that is actually angle EDB. In total, the sum of those two angles must be equal to 180 degrees according to the rule that I mentioned. So here we will subtract 90 degrees from this equation, and we will get that the missing angle EDB, is equal to 180 degrees minus 90 degrees, it is 90 degrees. Angle EDB equals to 90 degrees. So actually, we know that angle CDB, this angle equals to 90 degrees, and this angle also angle EDB, it is also equals to 90 degrees. And when we made the construction and extended the semicircle to a circle, we created another semicircle. This is the semicircle that we created, and actually the new semicircle that we created is the mirror image of the original semicircle. Okay, and then when we extended the straight line CD by straight line and created the line segment DE, DE is also the mirror image of the straight line CD. Why? Because angle CDB equals to 90 degrees, and then EDB it is also equals to 90 degrees. So DE is the mirror image of CD, and because of the fact that D is the mirror image of CD, we conclude from it that CD equals to DE. CD equals to DE by symmetry. Actually, it is exactly like if you look at yourself in a mirror, you see yourself exactly in the same dimension that you are in reality, but in the opposite direction. This is exactly true for segment lines CD and DE. DE is the mirror image of CD, but in the opposite direction. So the length of line segment DE equals to CD. Why? Because DE is the mirror image of CD. Okay? But here it is given us the question that CD equals to 3 units. CD equals to 3 units. And for this equation 3 equals to CD equals to DE, we will derive that DE is also equals to 3 units. D equals to 3 units. So here we can write down that D equals to 3 units. Okay. In the next step I will present to you a new rule that is actually rule number 1. According to rule number 1, if two chords intersect with each other inside a circle, or if chord AB intersects with chord CD at point O inside the circle, then the following equation is true. That AO times OB equals to CO times OD. I'll repeat again rule number 1. According to rule number 1, if chord AB intersects with chord CD at point O inside the circle, then the following equation is true, that AO times OB equals to CO times OD. So here we have chord AB, this is chord AB, that intersects with chord CD. This is called CD. It's point O. Again, chord AB intersects with chord CD. It's point O. Inside the circle, of course. So if this is the data that has been given to us, then according to rule number 1, AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Okay, point O is the intersection point of chord AB with chord CD. So we actually can implement rule number 1 in our drawing, because in our drawing we have this circle, and inside this circle we have chord AB that intersects with chord CE at point D. I'll write it down. In our drawing we have chord AB intersects with chord CE. This chord, it's point D. This is point D, that is the intersection point of chord AB with chord CE. So therefore, according to rule number 1, we will get that AD times DB equals to CD times DE. I repeat again. Chord AB intersects with chord CE at point D. Point D is the intersection point of chord AB with chord CD. Therefore, according to rule number 1, we will get that AO times DB equals to CD times DE. Okay? So here AD is the missing line segment, so we will leave it as it is. Times dB. dB equals to 4 units according to what is given us the question, so we'll substitute dB by 4. And it is equal to CD. CD equals to 3 units according to what is given us the question. Times DE. We already found out that DE equals to 3 units. So in conclusion, we found out that according to rule number 1, AD times 4 equals to 3 times 3. Or 4AD equals to 3 times 3, that is 9. Here we'll divide this equation by 4, and we get that AD equals to 9 over 4 units. Okay, so we found out that the missing line segment AD equals to 9 over 4 units. And we also know that if AB AB is the diameter of this circle and also the diameter of the big circle and also the diameter of the semicircles. And we also know that the diameter of any circle is twice as long as the radius. So obviously, if we divide the diameter AB to 2, we will get the radius of the big circle, so we'll define the radius of the big circle as capital R. So we found out that AB, the diameter over 2, equals to the radius of the big circle, that is capital R, according to our definition. But we also know that AB equals to AD plus DB, so we substitute AB by AD plus DB. And we divide it by 2. AD equals to 9 over 4. DB equals to 4. All divided by 2. So here we will multiply 4 by 4 and then we will divide it by 4 in order to have a common factor with 9 over 4. And we will get that 9 plus 4 times 4 is 16 over 4 over 2. 9 plus 16 is 25 over 4 over 2. Here we will move 2 to the denominator and we will get that the radius of the big circle is equal to capital R. It is equal to 25 over 4 times 2. 4 times 2 is 8, so in conclusion we found out that the radius of the big circle, that is also the radius of the semicircles, is equal to 4 times 2 is 8, so it is 25 over 8 units. Okay, the radius of the big circle equals to 25 over 8 units. In the next step, we will define the center of the big circle as point P, and we will define the center of the small circle as point Q, and we will find out the length of the short line segment DP. Okay. So here the length of the short line segment DP for the drawing, it is very easy to say that DP equals to DB minus PB. DB minus PB. Yes, dP equals to dB minus PB. So dP, the short line segment dP, it is equals to dB. dB is equal to 4 units according to what is given in the question. So we substitute dB by 4 minus PB. Here P is the center of the big circle, and B is the point of the big circle itself. This is exactly the definition of a radius. That is to say, PB equals to the radius of the big circle, that is equal to capital R. So in conclusion, we found out that dP equals to 4 minus capital R. But we already found out that capital R, the radius of the big circle, equals to 25 over 8. So we can substitute capital R by 25 over 8, and we get that in conclusion dP equals to 4 minus capital R, that is 25 over 8. So here we will multiply 4 by 8, and then we divide it by 8 in order to have a common factor of 25 over 8. And we get that dp is equals to 4 times 8 is 32, minus 25 over 8. 32 minus 25 is 7. So in conclusion, found out that dp equals to 7/8. dp equals to 7/8. Now here we can write down that dp equals to 7/8. In the next step, we will define the point of tangency of tangent CD with this small circle as point O, and we will define the point of tangency of this tangent DB with this small circle as point M. And from the center of the small circle, that is to say from point Q, we will draw the radius to point O, that is the point of tendency. First of all, YQO is the radius of the small circle. Why? Because Q is the center of the small circle and O is the point on the small circle itself. This is exactly the definition of a radius. So we define the radius of the small circle as small r, so QO equals to small r. So here we have the radius QO that is drawn to the point of tendency, that is to say the radius QO is drawn to point O, that is the point of tendency of tangent CD with this small circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent CD will be perpendicular to the radius OQ. So CD is perpendicular to OQ, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Okay, likewise, from point Q we will draw the radius to point M. QM is the radius of the small circle because of the fact that line segment QM starts from point Q, that is the center of the small circle, and point M is the point of the small circle itself. This is exactly the definition of radius. So QM is the radius of the small circle that is equal to small r. So here we have the radius of the small circle QM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent DB with this small circle, and whenever we have a radius that is drawn to the point of tendency, then the tangent DB will be perpendicular to the radius MQ. So if DB is perpendicular to MQ, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Okay? So actually in quadrilateral OQDM, we have 1, 2, 3 right angles. Okay? In quadrilateral OQDM, we have three right angles. The sum of three right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is actually angle OQM. In total, the sum of those four angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we will subtract 270 degrees from this equation, and we will get that the missing angle OQM is equal to 360 degrees minus 270 degrees. It is equal to 90 degrees. Okay? So actually, angle OQM is a right angle. This is a right angle. Therefore, quadrilateral OQDM is four right angles. And any quadrilateral that has four right angles, it will be at least a rectangle. So we will relate to quadrilateral OQDM as a rectangle. Quadrilateral OQDM is a rectangle. Quadrilateral OQDM is a rectangle. Quadrilateral OQDM is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, OQ equals to DM, OQ equals to DM, according to the rule that the opposite sides of a rectangle are equal to each other. So in rectangle OQDM, OQ must be equal to DM. But we know that OQ equals to small r. We can write here that OQ equals to small r. And from this equation, r equals to OQ equals to dm. We will derive that dm is also equals to small r. dm equals to small r. And here, dm equals to small r. And what is the value of Pm? Here the value of Pm, it is very easy to see from the drawing that here Pm equals to dm minus dp. I will put again, Pm equals to dm minus dp. Okay? So Pm equals to dm, dm equals to small r, according to what we have already found out. We will substitute dm by small r, minus dp. We have already found out that dp equals to 7/8. So we substitute dp by 7/8. And in conclusion, we found out that Pm equals to r minus 7/8. Here, Pm equals to small r minus 7/8. So I can write here that PM equals to small r minus 7/8. In the next step, I will present to you a new rule that is actually rule number 2. But before that, we have this point is a touching point between those two circles, or the launch point between those two circles. We define this point as point S. So point S is the launch point of the two circles. Why? Because in this point S they are touching each other, they are tangent to each other. So point S is the launch point of the touching point or point of tendency of those two circles, this big circle with the small circle. Okay, now I will present to you rule number 2. According to rule number 2, if two circles have an internal length between them, if two circles have an internal length between them, that is to say, in our original drawing, those two circles, the big circle and the small circle, have an internal length between them at point S. That is to say, because of the fact that the small circle is located inside the big circle, then this touching point is defined as internal launch point. That is to say, those two circles have an internal launch between them at point S. Okay? So, if two circles have an internal launch between them, then the straight line then the straight line that the straight line that connects their centers passes through the launch point. Passes through the launch point. So I read rule number 2 again. According to rule number 2, if two circles have an internal launch between them, then the straight line that connects their centers passes through the launch point. So what is the meaning of rule number 2? The meaning of rule number 2 is that in this case we have those two circles have an internal launch between them at point S. Therefore, according to rule number 2, we get that the straight line that connects between them is PQ. Why it is the PQ? Because of the fact that P is the center of the big circle and Q is the center of the small circle. Okay? So according to rule number 2, this straight line PQ passes through point S. This is actually the launch point between those two circles. Okay? So, according to rule number 2, we get that points P, Q, and S, they are all located on the same straight line. Points P, Q, and S points Q, P, Q, and S passes points P, Q, and S passes through the launch point. Points P, Q, and S are located on the same straight line. point Q and S, points PQ and S passes are located on the same straight line. So here points Q and S are located on the same straight line, or in other words, line segment PQS is a straight line. Okay, line segment PQS is one straight line. According to rule number 2, of course. Okay. So here, what is the definition of line segment QS? Q is the center of the small circle. S is the point of the small circle itself. Therefore, QS is defined as a radius of the small circle, that is to say, it is equal to small r. And what is the length of the definition of line segment PS? Here, P is the center of the big circle. S is the point of the big circle itself. This is exactly the definition of a radius. So PS is the radius of the big circle that is equal to capital R according to our definitions. But we have already found out that capital R equals to 25 over 8. So in conclusion, we found out that PS equals to capital R equals to 25 over 8. And what is the length of line segment PQ? Here PQ from the drawing itself, it is very easy to see that the length of line segment PQ it is equal to PS minus QS. Again, PQ equals to PS minus QS. So PQ equals to PS is the radius of the big circle that is equal to capital R. So we substitute PS by capital R minus QS. We already found out that QS equals to small r. So in conclusion, we found out that the length of line segment PQ equals to capital R minus small r. But we already found out that capital R equals to 25 over 8, so we can substitute capital R by 25 over 8. We'll do it now and we'll get it PQ equals to capital R is 25 over 8 minus small r. So in conclusion, we found out that PQ equals to 25 over 8 minus small r. So in the next step, I'll copy the main right triangle QPM in a new page and we'll implement the Pythagoras theorem on this green right triangle, triangle PQM, in order to find out the value of the missing variable, that is small r, the radius of the small circle. That is the question that we want to answer on this lecture. What is the radius of the small circle that is actually equal to capital R? So I copy the right angle Q PM in this new page. So this is the right angle QPM that I copied from the original drawing. We have already found out that QP equals to 25/8 once small r. So we can write here that the hypotenuse of the right triangle PQM is equal to 25/8 minus small r. And we have already found out that PM equals to small r minus 7/8, while QM equals to small r. Okay? So here we will implement the Pythagoras theorem on this right triangle, triangle QPM. So here I write down it is by PT, that is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, we get that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So the hypotenuse is PQ, therefore the square of the hypotenuse is PQ squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to QM squared plus PM squared. Okay? PQ equals to 25/8 minus R, so I write it down. So PQ squared is 25/8 minus R squared, and it is equal to QM squared. QM equals to small r, so QM squared equals to small r squared plus PM squared. PM equals to small r minus 7/8. So actually PM squared will be equal to small r minus 7/8 squared. So here we will open the brackets on both sides of this equation, equation number 1. And we get that according to equation number 1, we will open the brackets on both sides according to the algebraic identity that a plus b squared, a minus b squared equals to a squared plus b squared minus 2 times ab. So here 25/8 minus r squared will be equal to 25/8 squared, that is 25 squared is 625, over 8 squared is 64, plus r squared minus 2 times 25/8 times r. and it is equal to r squared plus r minus 7/8 squared is equals to r squared plus 7/8 squared is 7 squared is 49 over 8 squared, it is 64 minus 2 times r times 7/8. Okay, so here we have r squared on both sides of equation number 1, so r squared will get cancelled, and we left only with, according to equation number 1, we have 625 over 64 and here we have minus 2 times 25r over 8. Here we will divide both the numerator and the denominator of this expression by 2. So here minus 2 over 2 is minus 1, so 2 will get cancelled. In the numerator we left with minus 25r. In the denominator we have 8 that is divided by 2 is 4. So in conclusion, this expression equals to minus 25r over 4. And it is equal to r squared plus 49 over 64 and here we have minus 2r times 7 over 8. We will divide both the numerator and the denominator of this expression by 2. Minus 2 over 2 is minus 1, so 2 will get cancelled. So in the numerator we left only with minus 7r, and in the denominator we have 8 that we divided by 2, that is equal to 4. So in conclusion, this expression equals to minus 7r over 4. Okay. So here we multiply this equation number 1 by 64, and we'll get that according to equation number 1, 625 times 64 over 64 is 625, and here we have minus 25r over 4. If you multiply it by 64, we'll get that minus 64 over 4 is minus 16 times 25r. So in conclusion, this expression minus 25r over 4, after we multiply it by 64, it is equal to minus 16 times 25r, and it is equal to 64 times r squared is 64r squared, and here we have 49 times 64 over 64 is 49, and here we have minus 7r over 4 times 64, it is actually minus 64 over 4 is minus 16, and we have to multiply it also by 7r. Okay. So according to equation number 1, we found out that 625 minus 16 times 25 r, it is equal to minus 400r, that is equal to 64r squared, and here we have plus 49 minus 16 times 7r equals to minus 112r. So here we will add 400R to this equation number 1. And we'll get that here we have 625. And 400R minus 400R is 0. So in this side of equation number 1, we left only with 625. That is equal to 64R squared plus 49 and here we have 400R minus 112R. It is equals to plus 288R. So here we will subtract 625 from this equation number 1, and we'll get that according to equation number 1, 625 minus 625 is 0, and it is equals to 64R squared plus 288R, and here 49 minus 625 equals to minus 576. Okay, here we divide this equation by 32, and we get that according to equation number 1, (64) over 42 is 2, so in total this expression equals to 2R squared. And we have here 288R over 32 is 9R. And here we have minus 576 over 32 is minus 18. And here 0 over 32 is 0. So in conclusion, we got the quadratic equation, the 2R squared plus 9R minus 16 equals to 0, minus 18 of course, because minus 576 over 42 is minus 18. So in this quadratic equation, the coefficient A equals to 2, the coefficient B equals to 9, and the coefficient C equals to minus 18. And the variable that we are looking for in this quadratic equation is R, so X equals to R. And the general formula for the solution of quadratic equation is X equals to minus B plus minus square root of B squared minus 4 times AC over 2A. Here A, B, and C are the coefficients of the quadratic equation, and X is the variable that we are looking for. In our specific quadratic equation, the variable that we are looking for is A, so we substitute X by A. Is R, the radius of the small circle, so we substitute X by small r, so here small r equals to minus b, b equals to 9, so minus b is minus 9, plus minus square root of b squared. B equals to 9, so b squared is 9 squared, that is 81, minus 4 times a is 2, minus times c is minus 18. All divided by 2a, a is 2, so 2a is 2 times 2, that is 4. Okay. So actually found out that r equals to minus 9 plus minus square root of 81, and here we have minus 18, minus 4 times 2 is minus 8, and minus 8 times minus 18 is plus 144. So inside the root we have 81 plus 144 divided by 4. So R equals to minus 9 plus minus 81 plus 144 is 225. So inside the root we left only with 225 over 4. So here R equals to minus 9 plus minus the square root of 225 is 15 over 4. So here we will have two solutions that are possible for R. The first solution for R is that R, the radius of the small circle, it is equal to minus 9 minus 15 over 4. Minus 9 minus 15 is minus 24, and minus 24 over 4 is minus 6. So we found out that R equals to minus 6. That is a negative number, of course, but here R, or small r, is the length of the radius of the small circle, and r is a length, it must be a positive number. R is a length, and therefore it must be a positive number. It can never be equal to minus 6, that is a negative number, so we will cancel this solution, and we left only in the second solution that R equals to minus 9 plus 15 over 4. Minus 9 plus 15 is 6, and 6 over 4. Here we will divide both the denominator of 6 over 4 by 2. 6 over 2 is 3, and 4 over 2 is 2. So in conclusion, we found out that R, the radius of the small circle that we are looking for, it is equal to either 3½ units, or in terms of numbers, it is equal to 1.5 units. Okay, here R, that is the radius of this small circle, it is equal to either 3½ units, or in terms of numbers, it is equal to 1.5 units. So in the next step I will summarize the lecture. Actually, we wanted to find out the radius of this small circle that is located inside the semicircle. We know that CD equals to 3 units, DB equals to 4 units, and angle CDB, this angle equals to 90 degrees, and we want to find out the radius of this small circle. Okay, so in order to find out the radius of the small circle, we did a construction. We completed the semicircle to a circle, and in this way we actually created a second semicircle that is a mirror image of the original semicircle. I repeat again, the second semicircle that we created by completing the semicircle to a circle is the mirror image of the original semicircle. Yeah. By completing this semicircle to a circle, we created this semicircle that is the mirror image of this semicircle, the original semicircle. In the next step, we extended line segment CD by straight line until it touches the circle at point E. Point D is the touching point of the extended line segment CD in the circle. Okay? And here we actually extended the straight line CD by a straight line. In this way we created the line segment CE. And if you extend a straight line by a straight line, the result must be a straight line. So the result of the extension of line segment CD by a straight line is line segment CE. So the result that is CE must be also a straight line. So we wrote here that CE is a straight line. Because when you extend a straight line by straight line, the result must be a straight line. So the result that is CE must be a straight line. So we have the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on this side of the straight line CE at point D, then the sum of the angles here must be equal to 180 degrees. Okay? So which angles we have at point D of this side of CE? We have here 90 degrees plus angle EDB. So 90 degrees plus angle EDB must be equal to 180 degrees. We subtracted 90 degrees from this equation and found out that the missing angle EDB equals to 90 degrees. So this angle EDB equals to 90 degrees. And actually, as I've already mentioned, the second semicircle that we created by the construction is the mirror image of the original semicircle. And then after we extended line segment CD by straight line, we created line segment DE that is also the mirror image of line segment CD. Why? Because angle CDB equals to 90 degrees and angle angle EDB also equals to 90 degrees. For that reason, line segment line segment DE must be the mirror image of line segment CD. And because of the fact that line segment DE is the mirror image of CD, CD must be equal in its length to DE. Why? Because when you look in a mirror at yourself, you see yourself exactly in the same dimensions as you are in reality, but in the opposite direction. And exactly the same rule is true for line segment CD and line segment DE. Line segment DE is the mirror image of line segment CD, therefore the length of line segment DE and the length of line segment CD must be equal to each other. CD equals to DE by symmetry because of the fact that line segment DE is the mirror image of line segment DE, therefore they must be in the same length. That is to say CD equals to DE. Okay? But here it is given us the question that CD equals to 3 units. So we can write here that CD equals to 3 units. And from this equation 3 equals to CD equals to DE, we will derive that DE is also equals to 3 units. So this line segment DE equals to 3 units. In the next step, I presented to you a new rule that is actually rule number 2, rule number 1. According to rule number 1, if chord AB intersects with chord CD at point O, point O is the intersection point of chord AB with chord CD, then the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Okay? So we actually can implement rule number 1 in our drawing. Why? Because in our drawing we have line segment AB, this line segment, actually chord AB. We have this circle, inside this circle we have chord AB that intersects with chord CE at point D. Point D is the intersection point of chord AB with chord CE. I repeat again. Here we have, in our original drawing, we have chord AB that intersects with chord CE at point D. Point D is the intersection point of chord AB with chord CE. Therefore, according to rule number 1, we will get that AD times DB equals to CD times DE. Again, AD times DB equals to CD times DE. Okay, AD times DB equals to CD times DE, according to rule number 1, of course. So here AD is the missing line segment, so we will leave it as it is. DB equals to 4 units according to what is given as the question. CD equals to 3 units according to what is given as the question, and we have already found out that DE is also equals to 3 units. So in conclusion, we found out that according to rule number 1, 4 times AD equals to 3 times 3. 3 times 3 is 9, so in conclusion, we found out that 4 times AD equals to 9. We divided this expression by 4, and found out that the missing line segment AD equals to 9 over 4. Or you can present it also as 9 quarters. Okay? The length of this line segment AD equals to 9 quarters. Okay? So here we know that AB is the diameter of the semicircle and also the diameter of the big circle. And we also know that the diameter is always twice as long as the radius. So if we divide the diameter that is AB of the big circle, the diameter is AB. If we divide it by 2, we'll get the radius of the big circle that is defined as capital R. So according to the drawing, AB equals to AD plus DB. So we substituted AB by AD plus DB, and we divide it by 2 in order to get the radius of the big circle. AD equals to 9 quarters, BD equals to 4, all divided by 2. Here we multiplied 4 by 4, and also we divided by 4 in order to have a common factor. We find 9 quarters. And we found out that in the numerator we have 9 plus 4 times 4 is 16, so it is 9 plus 16 over 4 divided by 2. 9 plus 16 is 25. Divided by 4 and divided also by 2. So we moved 2 to the denominator, and we got that the radius of the big circle that is capital R, it is equals to 25 times 25 over 4 times 2. 4 times 2 is 8, so in conclusion found out that the radius of the big circle that is equal to capital R, it is equal to 25 over 8 units. Capital R equals to 25 over 8 units. Then we found out the length of the short line segment DP. Actually, first of all, we have, of course, defined the center of the big circle as point P, and we defined the center of the small circle as point Q. Then we found out the length of the short line segment DP. From the drawing, it is very easy to see that the length of line segment DP equals to DB minus PB. Again, DB minus PB equals to DP. Very simple. DP equals to DB minus PB. DB equals to 4 units according to what is given as the question. And what is the definition of line segment PB? P is the center of the big circle. P is the point of the big circle itself. This is the definition of a radius. So PB is the radius of the big circle that is equal to capital R. So we substituted PB by capital R. And we have already found out that capital R equals to 25 over 8. So we can substitute capital R by 25 over 8. So in conclusion, we found out that DP, the length of the short line segment DP, equals to 4 minus 25 over 8. Here we multiplied 4 by 8 and then we divided by 8 in order to have a common factor with 25 over 8. 4 times 8 is 32. So in the numerator we have 32 minus 25, that is 7, and in the denominator we have 8. So in conclusion, we found out that dp equals to 7/8. Here we can write that we know that the length of the short line segment dp equals to 7/8. Okay. Then we defined the point of tendency of tangent CD with this small circle is point O. This point is the point of tendency of tangent CD with this small circle. And we also defined the point of tendency of tangent DB with this small circle as point M. Point M is the point of tendency of tangent DB with this small circle. In the next step, from point Q, that is the center of the small circle, we do the radius to the point of tendency, that is to say, we draw the radius QO to the point of tendency, that is point O. First of all, the reason that QO is the radius of the small circle is because of the fact that Q is the center of the small circle. O is the point of the small circle itself. This is exactly the definition of a radius. So QO is the radius of the small circle that is equal to small r. And then, because of the fact that the radius QO, it is drawn to the point of tendency, that is to say it is drawn to point O, that is the point of tendency of tangent CD with this small circle, because of the fact that the radius is drawn to the point of tendency, then the tangent CD will be perpendicular to the radius OQ. So CD is perpendicular to OQ, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Likewise from point Q, we do the radius QM. Q is the center of the small circle, M is the point of the small circle itself, therefore QM is the radius of the small circle that is equal to small r. So here we have the radius QM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent DB with this small circle. And whenever we have a radius that is drawn to the point of tendency, then the tangent DB will be perpendicular to the radius MQ. So if DB is perpendicular to MQ, that is to say this angle equals to 90 degrees and this angle will be also equal to 90 degrees. So actually in quadrilateral OQDB we have 1, 2, 3 right angles. Okay, in quadrilateral OQD, actually it is quadrilateral OQDM, we have 1, 2, 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle that is actually angle OQM. In total, it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we subtracted 270 degrees from this equation, and we found out that the missing angle OQM equals to 360 degrees minus 270 degrees, it is 90 degrees. So the missing angle here, OQM, equals to 90 degrees. Therefore, in quadrilateral OQDM, we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle. So we will define quadrilateral OQDM as a rectangle. But we know that in a rectangle, the opposite sides of a rectangle are equal to each other. So in rectangle OQDM, its opposite sides are equal to each other. That is to say, OQ equals to DM. OQ equals to DM, according to the rule that the opposite sides of a rectangle are equal to each other. But we have already found out that OQ equals to small r. So we can write here that OQ equals to small r, and from this equation r equals to OQ equals to DM, we will derive that DM is also equals to small r. Here, DM is also equals to small r. Okay? And what is the length of line segment PM. From the drawing, it is very easy to see that PM equals to DM minus DP. Again, DM minus DP equals to PM. PM equals to DM minus DP. DM, we have already found out that DM equals to small r. It is the radius of the small circle. We have already found out that DP equals to 7/8. So in conclusion, we found out that PM equals to small r minus 7/8. Here, PM equals to small r minus 7/8. Okay? Then I explain to you that in this drawing we have an internal lunge between this small circle and the big circle. Why? Because of the fact that the small circle is located inside the big circle and the small circle touches the big circle at this point S. That is to say, those two circles have an internal lunge between them at point S. Point S is the lunge point of those two circles. So in this drawing, we have an internal lunge between those two circles. Okay? Then I presented to you rule number 2. According to rule number 2, if two circles have an internal lunge between them, then the straight line that connects their centers passes through the lunge point. Okay, so I read rule number 2 again. If two circles have an internal lunge between them, then the straight line that connects their centers passes through the lunge point. So according to rule number 2, because of the fact that in this drawing we have those two circles that have an internal lunge between them at point S, then according to rule number 2, the straight line PQ that connects the centers of those two circles must pass through point S. That is to say, PQS is one straight line. According to rule number 2, if we implement rule number 2 in our drawing, we will get that PQS is one straight line, or points PQ and S, they are all located on the same straight line. That is to say, line segment PQS is one straight line. Okay, here, line segment PQS is straight line, or points PQ and S, they are all located on the same straight line. So here, what is the definition of line segment QS? Q is the center of the small circle. S is the point of the small circle itself. This is exactly the definition of a radius. So QS is the radius of the small circle that is equal to small r. What is the definition of line segment PS? P is the center of the big circle. S is the point of the big circle itself. This is exactly the definition of a radius. So PS is the radius of the big circle that is equal to capital R. And we have already found out that capital R equals to 25/8. So in conclusion, we found out that PS is actually equals to 25/8 units. That is the radius of the big circle. Okay? And so PS is the radius of the big circle. QS is the radius of the small circle. And what is the length of this line segment PQ? From the drawing, it is very easy to see that PQ equals to PS minus QS. PS minus QS equals to PQ. I'll repeat again. Here, PQ equals to PS minus QS. We have already found out that PQ equals to capital R and QS equals to small r. So in conclusion, we found out that PQ equals to capital R minus small r. And we already found out that capital R equals to 25/8, so we can substitute capital R by 25/8. We did it and we got that PQ, in conclusion, it is equals to 25/8 minus R. So here it is actually the hypotenuse of the right triangle QPM that is equal to 25/8 minus R. Okay, so I copied the right green triangle QPM in a new page, and we implemented the Pythagoras theorem on this right green triangle QPM in order to find out the value of small r. Here, the hypotenuse QP equals to 25 over 8 minus small r. PM, we already found out that it equals to small r minus 7/8, and QM equals to small r. And according to the Pythagoras theorem, PT is the abbreviation for Pythagoras theorem. We found out that the square of the hypotenuse is PQ squared. It is equal to the sum of the squares of the perpendiculars. It is equal to QM squared plus PM squared. So here, PQ squared equals to QM squared plus PM squared. So PQ equals to 25 over 8 minus r. So PQ squared is 25 over 8 minus r squared. That is equal to QM squared. QM is r, so QM squared is r squared plus PM squared. PM equals to r minus 7/8, so PM squared equals to r minus 7/8 squared. So here we open the brackets on both sides of equation number 1, and we found out that 25 over 8 minus r squared equals to 25 over 8 squared, that is 25 squared, that is 625 over 8 squared, that is 64, plus r squared, minus 2 times 25 over 8 times r. And here we have r squared plus r minus 7/8 squared. R minus 7/8 squared equals to r squared plus 7/8 squared. 7/8 squared is 7 squared, that is 49 over 8 squared, that is 64. So in conclusion, 7/8 squared equals to 49 over 64 minus 2 times r times 7/8. Okay? Then here we have 2 times 25 r over 8. We divided both the numerator and the denominator of this expression by 2, and we got that is equal to minus 25 r over 4. Here we divided both the numerator and the denominator of this expression by 2, and found out that this expression equals to, after dividing it by 2, it is equal to 17r over 4. Then we multiplied this equation number 1 by 64, and we got that 625 over 64 times 64 is 625, minus 25r over 4 times 64 is minus 16 times 25r. And r squared times 64 is 64r squared. 49 times 64 over 64 is 49. Minus 7r over 4 times 64 is minus 16 times 7r. So here we have 625, and minus 16 times 25r equals to minus 400r. Here we have 64r squared plus 49, and minus 16 times 7r is minus 112r. Okay, so in conclusion, according to equation number 1, we found out that 625 minus 400r equals to 64r squared plus 49 minus 112r. Here we added 400r to this equation number 1, and we got here that 625, 400r minus 400r is 0. And so in this side of the equation we left only with 625. In the other side of the equation we have 64r squared plus 49. Here we have 400r minus 112r is 288r. So here we added 625 to this equation number 1, and we got that 625 minus 625 is 0. In the other side of the equation we have 64r squared plus 288r, and here we have 49 minus 625 equals to minus 576. So in conclusion, according to equation number 1, we found out that 0 equals to 64r squared plus 288r minus 576. We divided this equation number 1 by 32, and we got that 64 over 32 is 2. So this expression in total equals to 2r squared. 288r over 32 equals to 9r, and minus 576 over 32 equals to minus 18. So in conclusion, according to equation number 1, we got that 2r squared plus 9r minus 18 equals to 0. So we have here a quadratic equation. The coefficient A of this quadratic equation equals to 2, the coefficient B equals to 9, and the coefficient C equals to minus 18. And the variable that we are looking for in this quadratic equation is r. So x equals to r. R is the radius of the small circle. And the general formula for solving out the quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. Here a, b, c are the coefficients of the quadratic equation, and x is the variable that we are looking for. In our specific quadratic equation, the variable that we are looking for is r. So x equals to r. So we substitute x by r, and we found out that r equals to minus b. B is 9, so minus b is minus 9, plus minus b squared. B is 9, so b squared is 9 squared, that is 81. Minus 4 times a is 2, and c is minus 18 over 2a. A is 2, so 2 times 2 is 4. So here we got that r equals to minus 9 plus minus 81. Here we have minus 4 times 2 is minus 8, and minus 8 times minus 18 is plus 144. So inside the root we have left only with 81 plus 144 divided by 4. So r equals to minus 9 plus minus 81 plus 144 is 225 divided by 4. So r equals to minus 9 plus minus, the square root of 225 is 15 over 4. So here we have two solutions that are possible for r. The first solution for r is that r equals to minus 9 minus 15 over 4. Minus 9 minus 15 is minus 24, and minus 24 over 4 is minus 6. So we found out that r equals to minus 6, that is a negative number. But because of the fact that r is the radius or the length of the radius of the small circle, r is a length, it must be a positive number. So here r is a length, and this length, it must be a positive number. So r can never be equal to minus 6, that is a negative number. So we cancel this solution, and we left only with the second solution for r, that r equals to minus 9 plus 15 over 4. Minus 9 plus 15 is 6. So r equals to 6 over 4. We divided both the numerator and the denominator of 6 over 4 by 2. 6 over 2 is 3, 4 over 2 is 2. So in conclusion, we found out that r, the radius of this small circle, equals to either 3 halves, or in terms of numbers, it is equal to 1.5 units. I'll repeat again, r, the radius of this small circle, it is equal to either 3 halves, on terms of numbers, it is equal to 1.5 units. Okay? Thank you very much.